look at, there you go, inequalities of combined functions. So they've given us two functions, f at x and g at x. And they've asked us to find when f at x is greater than g at x, and vice versa when g at x is greater than f at x, which is, we'll discover we can kind of do really all in one mathematical move, I guess you would call it. One of the things we could do is graph our functions. If we kind of draw a rough sketch and then try to get key points along the way, that can be very helpful. Our first function here is just a linear line on a 45-degree angle. It's f at x equals x, right? So there's our very first function. That one's kind of drawn in red. Our second function, luckily we know, is a quadratic. This is technically a vertex form. This is your a value. They usually refer this to an h in quadratics, but when it comes to transforming functions, this is considered also the d value. And then our c value is unknown, and there is no k value in this case. K value essentially kind of does the same thing as the a value here. So with that being said, the a value is 1, so there's no vertical stretch or compressions. C value 0, so we're not vertically moving it up and down or whatever from the original being this shape, x to the power of 2. What we are doing is moving the vertex, though, 2 units to the right. Since our d value is -2, we'll go over 2 units to the right, and if you remember graphing quadratics, this is 2, 1, 3, 4, 5, 6, and this is 0. You go over 1, up 1, so these two connect here. Over 2, up 4, 1, 2, 3, 4. 1, 2, 3, 4. And let's see, I'm going to make sure this line is drawn properly. It would technically go like that, this line. That would be our line. So let's be very exact since we are sans graphing calculator right now. Okay, so here are our two functions, and this is a point of intersection. Graphically, we can see, and we're lucky because it's simple enough that we can see that one of the points of intersection is at 1, 1. Another point of intersection is at 4, 4 is it? Yeah, 4, 4. So we have our 2 points of intersection here. Right away, we can tell when, and let's underline them, our G is in blue and our F is in red. Okay, so when f at x is greater than g at x, well, that occurs from here to here, okay? All of this space here, or from this x value to this x value, so if you kind of make it like this, you can tell that the f function, the one in red, is above our blue function, okay? So that means it is greater than g at x. Anywhere outside of that, okay, so when our x value is less than 1, so that's anywhere to the left of this, the blue function, our g function, is greater than our f function, which is our f at x. Okay? So whenever x is less than 1, this is occurring. And whenever x is greater than 4, this is also occurring. The g function, I know I didn't extend it, but you would see that the g function would be above where the linear function is. Okay? So this graphically, we can see those ideas. And it would never be x is less than and equal to in this case, because when it's equal to, they're actually both equal. It's neither greater or less than. So in this case, we'd say when x is greater than 1, and when, sorry, did I say that right? No, I didn't. When x is greater than 4, and when our x value is less than 1, sorry, when our x value less than 1. That's when these two ring true. And for our f at x to be true, that's when our x is greater than 1, but less than 4. Okay, so the opposite of what we have down here for this to ring true. Another way we can go about doing this is we can actually subtract the functions from each other. Now, the order we subtract it in will determine which of the two of these we're solving. Okay, so for instance, since we've called them f at x and g at x, if I decide to subtract f at x minus g at x, okay, when this happens, whenever this new function, we'll call it h at x, okay? This would create a new function, h at x. Whenever that new function is greater than 0, okay, that would mean that the f at x is larger than the g at x. In other words, we're solving for the first idea, when f at x is greater than g at x. If we did the opposite, and we solved g at x subtract f at x, we'll call our new function what I will call it j at x. Whenever that's greater than 0, that would make the other thing too. Whenever g is greater than f at x, whenever it's positive, we know that g at x is greater than f at x. So which of these would you like to choose? Number 1 or number 2? Number 1. Okay, so let's take number 1. So I'll call it our new function h at x here. Our new function is equal to f at x was the value of just x. Okay, and we're going to subtract our g at x, which was x minus 2 squared. Okay, so let's expand. We'll FOIL here very quickly. This becomes x squared minus 4x plus 4. And then we distribute the negative into all three values. So we have x subtract x squared plus 4x plus 4. And when we simplify, we have negative x squared plus 5x plus 4. Okay, so we've...
Doesn't that one become negative 4?
Yes, it does. Thank you. And subtract 4. Very good. Negative and negative. Anything else right? Okay, so we have another quadratic. So this quadratic, now when we graph it, and because it's in standard form, it's hard to tell. But we do know that it's a negative, so it faces down somewhere. And since we already know that there is a point where these two do switch, we have some quadratic, and this is what it's going to prove. Okay, so at whatever the x-intercepts are, when we're positive or above the x-intercepts, that's when our, because we use this function, that's when f at x is greater than g at x, okay, whenever we're positive. And whenever this function is negative, okay, so whenever we're below the x-axis, that's when g at x will be greater than f at x, okay. So we've essentially set this, so really all we have to find is our x values, our roots of the function. And we already know what they are from above. Do you know what they're going to be? Where did our function switch? What were the x values?
1 and 4.
1 and 4. So before we even do this, those are going to be our values, 1 and 4. But let's factor here. Okay, can we? What style of factoring did you learn, or do you want to just do the quadratic formula? Decomposition. Okay. Yeah, let's do decomposition.
Or if it's without yeah, if it doesn't have a value that's not 1, then you just write it.
Yeah, it's whenever the a value is technically a positive 1, right? Because this one's negative 1, we'll probably have to use our decomposition, okay? So normally we look for two values that multiply to a times c, right? Which is negative 1 times negative 4, so positive 4. And those same two values need to add to our b value, which is positive 5. So pretty simply, we have our values of 1. Oh, no. Yeah, that's right. Oops. 1 and 4. So when we take our function, we have negative x squared. We have plus 1x plus 5x minus 4. Okay. We can factor out negative x here. Will that help us? Yes, let's factor out negative x. We factor out negative x, that leaves us with x minus 1. And oh, sorry, that's why. The value should have been 4, not 5. I wrote 5 in. It's all right. Caught our mistake. We can common factor out a value of 4. So if we common factor out our positive 4 here, we'd be left with x minus 1 again. Okay, and when we do that, these two become common factors. We have x minus 1 and negative x plus 4. If you were to set these equal to 0, you get x is equal to positive 1, and here you'll get x is equal to positive 4. So those would be our x-intercepts, and we already know between them is when f at x is greater than g at x, and vice versa when we're on the bottom. So that's algebraically a way we can solve it, along with graphically solve. For functions, here's our f at x, our linear, and then here's the quadratic, and they intersected at 1 and 4 x values, and you can notice the g at x is greater than the f at x, and then between 1 and 4, f at x is greater than g at x, and again, like we said before, g at x is greater outside of it. If we subtract f at x from g at x, you'll notice that its x-intercepts are right at 4. I'm just going to draw this linear line to show you that they coincide with each other, like when our other functions cross. And it shows you whenever this function is positive, so above the x-axis, that's when f at x is greater than g at x, because we subtracted f at x from g at x. And whenever it's below, g at x is greater, or it is less than that. And that was the function we got. You'll notice it's the exact same. Had we done it the other way and subtracted g at x from f at x, still the same idea. The x-intercepts haven't changed. So again, where the two functions cross, it's the exact same. But this time, it shows you, because we did g at x subtract f at x, anytime it's positive, so when it's less than 1, it's greater than f at x, and when it's greater than 4, it's g at x is greater than f at x, and then between 1 and 4, that's when f at x is greater than g at x. So kind of just to show you all the functions together here. That's what it would look like.